Thank you for waiting, everyone. Let's get started with ECE 20002 today. Here's what we're going to do. We're going to work through some of lecture set 6, get a little bit further along, and then at 10:20, we're going to switch gears and deal with any questions we have and do some review for the exam. So we'll do half, new material, half questions for the exam. So without further ado, I will share my screen and we will do some discussion on the frequency responsive FET amplifiers. Now we are ready to move on to the high frequency responsive FET amplifiers. So this picture should be familiar to, most of you, hopefully all of you. But this is, our diagram of an N-channel MOSFET. And I guess I didn't ever show this picture explicitly before, but this is the saturation mode, where now we have a pinched off channel right here. It goes to a single point at the drain. And then, of course, we have our two wells of N+ type silicon surrounded by depletion region. And then we have our P-type silicon substrate. We have our source and drain terminals. We have our gate and our body. Body and source are shorted together. Gate has some DC voltage applied to it. And now we're applying some voltage to the drain as well, such that we have VDG equal to the threshold voltage. So let's use this diagram to make some arguments about the origins of MOSFET capacitances. So the large signal MOSFET model used the gate channel capacitance, 2/3 Cox W times L. Remember, Cox is the capacitance, caused by the separation of charge at the gate, and that, that wants to well up under the drain, well up under the oxide layer of the channel. So the separation of charge leads to a capacitance. You get a factor of 2/3 after some calculus. Cox, remember, is oxide capacitance per unit area. And then W times L is the width into the page times the length of this channel. So that kind of makes sense. So we're going to need more capacitances to account for the finite time to charge and discharge the different MOSFET regions. It takes time in order to, cause charge to move across to these regions and, establish changes in their charge. So there are 4 choose 2 or 6 possible capacitances that could exist pairwise between the terminals. However, there's hardly interaction between the gate and the body or between the source and the drain. So we only really need 4 capacitances to fully characterize this. So we're going to need CGS, CGD, CSB, and CDB. So gate to source, gate to drain, source to body, and drain to body capacitances. So CGS and CGD, the ones at the top, come from the gate field effect, the origin of the transistor's name. But CSB and CDB come from the depletion capacitances from the p-n junctions within the device. So yeah, we have these p-n junctions, so we have a separation of charge. These are reverse bias, so we need depletion capacitances. Maybe you talked about depletion capacitance and junction capacitance in ECE 20001 when you were talking about semiconductor physics. If not, we will just throw some equations up and say these are good enough to calculate them. Most of the time, we're not even bother calculating the capacitances from the MOSFET model. We are just, dealing with them as, measurements that have been given to us. So because we have, substantial gate to source region overlap, we're going to get, and by overlap, I mean, you can see where the oxide overlaps the well a little bit. So because there's that overlap, we get this sort of overlap length LOV right here. And part of this is, even if you're very careful about implanting, this highly concentrated, the high concentration of donors is going to, cause the donor atoms to, diffuse outwards throughout the crystal. So you're going to get some overlap length no matter what you do. So we say that the overlap length is between 1/20th and 1/10th of the overall channel length. That's just a good rule of thumb. I said, split the difference, 0.075 times the length is the overlap length, basically. And you get one on each side. So that explains some of where the gate to source voltage comes from and the gate to drain capacitance come from. We can basically say the overlap capacitance due to this is, W times L overlap times C aux. So the width into the page times the overlap length times the gate to oxide capacitance. Now that gives us the overlap capacitance. And in the case of the gate to drain capacitance, that's all we have because the channel's been pinched off. So we don't even get much of a gate to channel capacitance. Whereas on the source side, because the channel is, full width there, we get the full gate to channel capacitance, 2/3 C aux W over L, or W times L rather, plus the overlap capacitance, because those capacitances act like they're in parallel. And now we get depletion capacitance. So this is a 3D image. So not only do we get it from the bottom, depletion region that you see here along the bottom of these N plus type wells, but you also get it from 3 of the 4 side walls, I should say. So the one coming out of the page, the one on the left of the source region, behind the source region, coming out of the page in the drain region, to the right of the drain region, behind the drain region, but you don't get it from the 4 side wall, the one that faces the channel, because generally the depletion is very large, so you don't even bother figuring out that capacitance contribution. So you get these equations for the internal MOSFET capacitances, CGS, this one, gate drain capacitance, source to body capacitance is a depletion capacitance, where we have CSBO, the zero bias source to body capacitance, and then we have quantity 1 plus VSB over V naught in the denominator to the MJ, where MJ is the grading coefficient. VSB is the voltage between the source and the body. Typically, we will want that to be 0. And then V naught is the built-in potential of the PN junction right here, which hopefully you covered that back in ECE 20001. So we could, get that equation if we want to. You can calculate it as, the thermal voltage times the log of the product of your 2 doping concentrations divided by your intrinsic concentration of carrier squared. Wow, I remember that. That's pretty good. MJ is the grading coefficient, again, 0.5, so we're basically taking one constant over the square root of something. The drain to body capacitance is, it's very similar. It's the zero bias drain to body capacitance over the square root of 1 plus VDB over the built-in potential, where VDB is probably some non-zero value because the source and the drain and the body are not tied together, just the drain and the source. So CGS tends to be the largest, tens of femtofarads. It's the king of these, whereas the rest are typically in the single femtofarads. And remember, a femtofarad is 10 to the minus 15th farads. So these are tiny capacitances we're talking about. What questions do we have? My screen is flickering a little bit. Hopefully I maintain connection. It's called the grading coefficient because it's related to how much you grade or create a gradient in the doping. So in our diagrams, we do pretty abrupt junctions where basically, we dope such that, it just cuts off right there. If we were to do a very gradual junction where you literally transition the doping from M plus to intrinsic, then you would get a different grading coefficient. And then if you do a hyper abrupt junction, which is another type of junction, you would get a different grading coefficient. So if I remember right, and this is where I'd have to look up some of my notes, I believe you get MJ is equal to 1 for hyper abrupt junction, and MJ is equal to 1/3 for a graded junction, linearly graded junction. And of course, this may not be known a priori. You may have to take measurements to figure out which type of grading coefficient best fits your specific MOSFET. So this could be thought of as a partially empirical model. Yeah, you would need like a curve tracer to figure this out, CV curve tracer. Okay. So there is one complete MOSFET high frequency small signal model. So this is, in a sense, the MOSFET small signal model because it includes high frequency effects. It'll work at low frequencies. The only problem is it's kind of a lot to take in. So instead of having an open circuit between gate and source, we now have a capacitance CGS with VGS across it. We have our normal GM VGS, dependent source in the small signal model, where GM is the FET transconductance. We have our normal early effect output resistance R naught, between drain and source. Also between gate and drain, we have CGD. We've included the body terminal separate, so we need CSB, its capacitance, and CDB, its capacitance. And we measure VBS to create this over here, which is a second dependent source, GMB VBS, where GMB is the body effect transconductance, yes. And VBS is obviously the body to source voltage. We call this effect where we have a second one, the body effect. It's something that we have left out of our discussion when we did MOSFETs because we already had like 92 slides and I didn't want to add in something that was rather extraneous. However, to be complete, we need this so-called back gate of the MOSFET. It's called the back gate because it's like having a back door to your house. It's another way to get into interesting MOSFET behavior without having to rely on using a gate to source voltage. So this is good for SPICE, bad for hand analysis. Like, yeah, I can program this in SPICE as a macro model. It would work very well. However, hand analysis, it's going to take us a very long time to solve even a simple problem with this MOSFET model. So what we're going to do is, say the body is connected to the source, so we short out CSB. That also means CDB falls across here. This dependent current source becomes an open circuit, and we're left with everything else. So this is the MOSFET high frequency small signal hybrid pi model. So this is what happens if the body is connected to the source. So we get CGS, CGD, GMVGS, R naught, or excuse me, R sub O, and CDB. Now, even your textbook neglects CDB most of the time. And most of the time, you just say, okay, we have the small capacitance between drain and source when we can ignore the body effect. So what we're going to do is just say, this is part of our load the same way R0 usually becomes part of our primed load resistance. This will become part of our primed load capacitance. So now we have to deal with both resistive and capacitive loads in our circuit. Great. But the main thing is, the open circuit of the hybrid pi model became this capacitance. And we also have this other bridging capacitance between gate and drain. And remember, for low frequency or even medium frequency work, we do not need the full high frequency small signal hybrid pi model. You can get by using an open circuit, for these capacitances and everything works out fine. Now, for those of you who aren't hybrid pi purists, we also have our high frequency small signal equivalent T model. So again, same information as the hybrid pi model. Some people don't believe me about this, but yes, you will get the exact same accuracy of answers when you use the equivalent T as the hybrid pi model. And again, this only works if the body's connected to the source. You'll see, okay, we have the regular hybrid or equivalent T model stuff, the gate, a VGS between this point and there, GM VGS that forces the same amount of current to flow down through the drain right here as does through this resistance 1/GM, which is very much a real part of the model. You can't neglect it. You have to have 1/GM in your model if you use the equivalent T model. We also have R sub O, the early effect output resistance here. And then we add in our three capacitances, CGS, CGD, and CDB, sometimes neglecting CDB when needed to simplify analysis, or saying it's part of our load capacitance, depending on our configuration of our circuit. And it's easier to use this equivalent T model whenever you have some sort of external impedance connected to the source. So something, the source terminal isn't tied directly to a supply terminal. Probably want to use the equivalent T model to save yourself some work. Otherwise, you're going to have to apply your probe voltages and measure the probe currents in order to find your input resistance and output resistance effectively. So a MOSFET data sheet should list the transition frequency as well, F sub capital T, also known as the unity gain frequency, where the short circuit current gain of the common source amplifier configuration becomes 1. So analysis used the high frequency hybrid pi model. So I will leave that up while reading from the slide. So we have the output short circuit current. So when the input is short circuited, we're going to get GM VGS. Output is short circuited. So we don't have to worry about the early effect resistance or this capacitance right here. So GM VGS is going to be part of the current, but we also have to, flowing out of the drain terminal, but flowing into the drain terminal is also the current through this capacitor, S times CGD VGS. So to, keep consistent with, the output. So we'll say, output current is GM VGS minus SCGD VGS, approximately equal to GM VGS. So CGD, like I said, is one of the smaller capacitances that hardly any current is going to flow to it up until this unity gain frequency we want to find. So we'll just make an approximation. Output current is just GM VGS. All the current flows through this dependent source. By KVL, we get that I in is equal to SCGS plus CGD, or because we short circuited the output, we can just take this in a loop. So we combine and substitute S equals J omega to get I naught over I is equal to GM over omega quantity CGS plus CGD. And we set that equal 1 to get the unity gain frequency. And then we usually report it, or we normally have our data sheets to do it as a linear frequency, not a radial frequency. So we get F of T in Hertz is equal to GM over 2 pi times CGS plus CGD. So notice that if we have the unity gain frequency and we can calculate GM for a given drain current, this basically tells us what the sum of these two important capacitances is. What's the interpretation of FT? Again, it's where we're working at such a high frequency in the hundreds of megahertz or tens of gigahertz that we've basically run out of gain. There's no more current gain to be had. We've eaten it all up trying to go into higher bandwidth rather than have gain. The other interpretation of the transition frequency is that the MOSFET is going to have a higher gain bandwidth product. So in other words, it works as a better amplifier transistor. So it's something that you can use to set apart how good a given MOSFET is at being an amplifier. Because again, it's really hard to change the gain bandwidth product. So something that, intrinsically has a better FFT means it has a lower capacitance or a higher FET transconductance, tells you it's a better amplifier. And then here's a good slide to start. Slide number 33. It's a summary of everything. So it's got the complete MOSFET high frequency model. Tells you how to calculate GM with the 3 different equations we have for GM. One that uses VOV, one that uses ID, and one that uses both. Tells you how you get GMB. You have to be given a parameter called chi. And then tells you how to calculate the early effect resistance, CGS, CGD, CSB, CDB, and the transition frequency. No, USDU's equivalency model. Yeah. There are MOSFETs that can handle fairly high frequency work. However, there are BGTs out there that can be used for almost terahertz applications, so hundreds of gigahertz. This is like this is used in circuits that are used to amplify signals that are in the super high frequency range. So like inside routers and for radar and for very high frequency communications. Does that answer your question, Aubrey? Yep. Yeah, BJTs have two areas where they're used: very high speed and very high current. We haven't gotten rid of them. They still dominate in certain aspects. And that's why I have lecture set J1 that talks about BJTs for those who are so interested. We cut them out of the curriculum. I think that's a shame. I got to keep going, otherwise I'll never get through this. So here is the high frequency hybrid pi model of the common source amplifier. We've gotten to the point in this class where not only are we assuming that you can, make a small signal circuit perfectly given the circuit, we've gotten to the point where you can be like, okay, all right, here's what it would look like even if we're not drawing the circuit. So here's just the small signal model. So here we got our Thevenin equivalent source. We got our equivalent biasing resistor outside. Source is grounded. Always remember to ground your terminals if it's supposed to be grounded. We have our hybrid pi model in the middle with CGS, CGD, and GM, VGS, and R sub O. And then we have our external resistors, RD and RL. Well, what we can do is, again, we know we're dealing with high frequencies now, so we needed the high frequency model of our hybrid pi model. And the body is shorted to the source, so we don't need the complete model. That's fine. Capacitors are going to have admittance, S times CGD. We'll deal with admittances when we need to. And then by Thevenin's theorem, we can replace, everything to the left of CGS with a single voltage source and single resistor. So I'll get V sig prime, R sig prime, where V sig prime is, RG over R sig plus RG times V sig. And R sig prime, remember to Thevenin's theorem, we turn off sources when we're finding the equivalent Thevenin resistance. So R sig prime is just R sig parallel RG. And then by parallel resistor formula, RL prime is R sub O, RD, RL in parallel. We're left with this circuit, which is a little bit more tractable looking. But, you know, we can find the mid-band gain. This should be possible when all the capacitors act as open circuits. So we'll get, RG over RG plus R sig times negative GM RL prime, which is what you would expect right here. So analysis can go super fast once we're down to this level of model. So the transfer function of the gain is of the form V, if we're being formal about it, VO over V sig equals CGD RL prime, quantity S minus GM over CGD over AS squared plus BS plus 1, which is the form of a second order low pass filter. Because, this zero is at relatively high frequency compared to the complex poles. Now, transfer function coefficients A and B are messy, defy intuition. We could write them out, but it's not really going to tell us very much. An approximation would serve the working engineer better. So the approximation needs to make IGD flow to the right of node G and decouple input and output while preserving the effect of CGD. So we need to peel off IGD current from the input side of the circuit, inject it into the output side of the circuit without having to deal with this bridging capacitance CGD. And to do that, we'll need something called Miller's theorem, but we are now traipsing into our time for discussing exam 2 review things and other things you have questions about in this course. So I will make a note that next lecture, probably the one on Friday, we'll discuss circuits in Miller's theorem and the high frequency effects. Alfred is amazing. Okay. So I will close out of the lecture set. What questions do we have about the exam? Format-wise, pretty much what you expect, except now you'll get a 20-minute grace period instead of a 15-minute grace period. That should reduce the number of mishaps that we have about people not being able to, upload their files because they ran out of time. But other than that, it's a 1-hour exam. Once the timer runs down, it'll stay at 0, and you'll have that time to upload your exam to Brightspace. Allowed to use calculator, straight edge. There is a fair amount of graphing on this exam. I recommend a straight edge. Calculator cannot connect to the internet. All right, what questions do we have? Or do you just want to see me go through what I have prepared, which I have 2 convolution examples prepared and 2/3 of a inverse Laplace transform problem. Anyone want to speak up? Yes, homework 3 to 5 are the ones to review. And people always ask me what my advice is for studying. I put it in the syllabus in the exam section. So if anyone's like, how should I best study for this exam? Like, I put it in the syllabus because it's something that gets asked a lot. Let's work on my problems. I always, struggle to answer the question, is the exam harder than homework? Maybe conceptually, you're more likely to encounter a thinking trap. Like, we throw in a signal that's U of t plus 2, but that's before the causal point of our one-sided Laplace transform at 0. So you have to, treat it like it's U of t instead of U of t plus 2. Maybe you run into a few more traps like that, but calculation-wise, it should be a little easier to perform. AJ, bandwidth problem, not completely series or parallel. I don't have that prepared yet. That's something I do want to do tomorrow. Shoot me a reminder on Piazza and I'll make sure I get it done. Homework solutions should be posted today. The TAs are working pretty furiously on getting number 4 up, and number 5 should be up a few hours after that. If there's anything you want to review from the homework, do let me know. That is fair game for tomorrow. But I will probably go ahead and show you what I have. Hopefully everyone can still see my screen. So here are the problems I plan on talking about. So we'll do a continuous time convolution. Wait. So I will force quit preview. And then I will open homework review. Oh man, even Alfred's having trouble force quitting preview. Open homework review exam 2. Perfect. So, okay, here's what we're going to do for review of exam 2. I have continuous time convolution done, graphical convolution, and most of the inverse Laplace transform done. And I don't have any of these circuits done. So the circuits where it'd be like, okay, solve with impedance and admittances, this circuit, even with initial conditions, blah, blah, blah. So don't have that done. But I do have the convolution problem, so we can at least go through them. So let's, is this best? This is best. We'll go big. So find the output y of t to a linear time invariant system with impulse response h of t equals h e to the minus at u of t, receiving an input x equals rt minus r of t minus 1. Find your answer without using Laplace transforms. So darn, we can't use Laplace transforms to figure out this problem. However, we know this is a linear time invariant system. So we know that the output y of t is x of t convolved with h of t. And we're going to work purely symbolically for this problem. So r of t is just t times u of t. So in tau land, it's going to become tau u of tau minus u of tau minus 1, u of tau minus 1, where in both places, both out front and in the step function, we have used t minus 1, which became tau minus 1. And then times h of t minus tau. So h of e to the negative a quantity t minus tau, u of t minus tau, all d tau. Is everyone good with this definition of convolution? So on the exam, feel free to, basically jump from h of t, x of t, tell me what convolution is, what you're doing, and then show me your convolution integral. That's fine. Like, you don't have to be, you should show all your work, but, don't make it so that, one step takes, 5. Unless, of course, you're the kind of person who needs to show all the intervening steps, in which case, write fast, don't get a cramp. So, well, h is just a constant factor, so we can pull it out of the integral. And then we can break up this term right here. What is it we break up? Okay, so we break up the tau and the minus tau minus 1. We can break these up into separate integrals. So we'll have tau u of tau e to the negative at e to the plus a tau u of t minus tau d tau minus h integral from negative infinity to infinity tau minus 1 u of tau minus 1 e to the negative at e to the plus a tau u of t minus tau d tau. We broke up the integral. And then we can change the bounds of our integral using these step functions. And we can also pull out e to the minus at out of both because it is not a function of tau. So it acts as though it's a constant with respect to the integral. So h e to the minus at, integral from 0 to t of tau e to the negative, or e to the positive a tau d tau, minus h e to the negative at, integral from 1 to t of tau minus 1 e to the plus a tau d tau. We can do integration by parts, IBP, on the integral in the first term right here. So let's see. It's always integral over your bounds u dv. So we want to reduce the order of tau d tau. So we will say u is equal to tau, and dv is equal to e to the plus a tau d tau. For those who can't remember there's like the Liotte rule, or for choosing which thing you want to differentiate. There's also the detail rule for choosing what you want to integrate. Those are acronyms, by the way. And then, we can also say dv is e to the plus a tau d tau. So when you integrate that, you get v is equal to 1 over a e to the positive a tau. Integration by parts formula, u dv is equal to uv evaluated minus integral v du. So tau e to the a tau d tau is equal to 1 over a tau e to the positive a tau 0 to t minus 1 over a integral 0 to t e to the positive a tau d tau. We can just plug things into the first thing right here. So plug in t where we see tau, 1 over a t e to the positive a t. When we plug in 0, we're going to multiply by 0 out front, so we just subtract off 0. And then minus 1 over a, evaluate this integral, which is 1 over a e to the a tau, evaluate between 0 and t. So all in all, we'll factor the 1 over a out and get t e to the at minus 1 over a e to the at plus 1 over a, because remember, the hardest thing to remember in this class sometimes is that e to the 0 is just 1. What questions do we have? Yeah, I'll get the draft posted ASAP, and then I will try to get the final version that I use tomorrow posted tomorrow night. So you'll at least get one version tonight. It just takes me a while to prepare these. Like, it really does take me a long time to go through example problems, and I'm trying to do a lot of them for you, because I care. So that was the first integral. We have a second integral. However, rather than go through integration by parts, we're saying it's going to be very similar. So we argue its results can be written by inspection from the first integration by parts. U is now tau minus 1, and we have a different lower bound of 1 instead of 0. The rest is the same. So we argue by inspection 1 over a in bracket quantity t minus 1 e to the positive at minus 1 over a e to the at plus, and then when we evaluate this with a lower bound of 1, we get e to the a over a. So we got these integrals. When we insert it back here, we should reinsert our step functions for the first term and the step function for the second term. The step function for the first one, uses u of t. The one for the second term uses u of t minus 1, because that's kind of what we were dealing with earlier. So you'll get h e to the negative at 1 over a, this right here, times u of t, minus h e to the negative at 1 over a times this right here in brackets, u of t minus 1. The rest is just algebra. So maybe I want to factor h out and an a squared out in the denominator out of everything. E to the minus at will cancel out with e to the positive at wherever it happens to produce a factor of 1. We needed to add a factor of a here, so we get at plus over here e to the minus at minus 1. all times u of t, then minus a times t minus 1 minus 1 plus e to the negative a quantity t minus 1, where that required some simplification. E to the minus at times e to the minus a is e to the minus at plus 1, but I factored the minus a out of everything, so it's minus a quantity t minus 1, all times u of t minus 1. And that is our answer. What questions do we have? Does everyone feel comfortable with integration by parts? So I'll give you a hint. The most you'll be asked to use integration by parts is once. You won't be asked to use it 2 or more times on the exam. It just takes too long. Iolate. Don't you mean liate? Backwards, including differentials, is detail. Where usual preference for integrating is differentials, exponentials, trigonometric, trigonometric, algebraic, wheels, inverse trig, and misspelled logarithms at the very end, but you get what I'm saying. Any other questions though? If not, we will do what is everyone's favorite thing, especially IBP formula on equation sheet. I'm going to say no to that. You know, that isn't something that is, you know, part of it. Just like I don't give you like how to do partial fractions on the equation sheet. I'll consider that part of your core math background, something that you should commit to memory. Hopefully it doesn't, you know, hopefully no one else asks you to have it committed to memory, but like it's better to have it memorized than not. Let me tell you, like integration by parts does show up like in your life as an electrical engineer or as a computer engineer. All right. Time for Riyadh's favorite thing, graphical convolution. Pretty sure it's Riyadh. Adrian isn't here. He likes it too. So let's convolve these two signals. So we have an input x of t is this rectangular pulse between 1 and 1, fed into a linear time invariant system with this trapezoidal impulse response h of t above. So graph the output y of t without leaving the time domain. Shucks. Even if we wanted to try to rewrite these as a combination of ramps and steps, you know, we're told we can't leave the time domain. So, you know, we can do it. We can do it algebraically. However, we're going to find that because it's just ramps and steps, graphical kind of is the way to go. So without leaving the time domain. So here's what I would do. And this problem is a little bit more complicated than something that I might throw on the exam, but probably better to show you something that's a little too complicated than not complicated enough. If I were doing this as an exam problem, you know, maybe I would get rid of this trailing edge right here where it goes down, and maybe just say, okay, it ramps up and then it stays flat. That might be a simpler problem to do. So, because we'll find that, there's basically 7 cases, 2 of which are 0, and 5 of them require graphs. So it's a little bit much. How do we know how many there are? You just kind of keep shifting things along mentally until you find out. But it's based off of how the width of one of your signals compares to the, separation of features in your second signal. And the answer is, well, it is separated enough, but like you get 1, 2, 3, 4, 5 different regions that are non-zero. So function collision at t equals 0.5. So for t equals 0.5, and anywhere between 0 and 1 really, we get that, okay, we took x convolved with h, but rather than flip h around, which is definitely a nightmare to have to shift, x is definitely the much easier function to shift. And because, remember, convolution is commutative, I can choose which function I reflect and shift. So I reflect this. So when I reflect this in tau land, it would start at 0 and then go back to -1. And then as I move forward in time, it moves to the right. So this leading edge right here is at t. This trailing edge of the red x to t minus tau is at t minus 1. What is the amount of overlap area between these two signals? Well, if you look right here, where the blue and the red overlap and are non-zero, they make a triangle. The formula for the area of a triangle is 1/2 base times height. So we'll get 1/2 the base, which is right over here. And then the height is going to be 2t because it's, determined by how tall you are along here. So this, line follows the equation 2t. And then this, base is, has a height of 1. And, the length is at t minus 0 because this leading edge is at t and it starts at 0. Can we follow this function collision? Yeah, so the best way to do graphical convolution is kind of a hybrid of graphical and algebraic techniques where you're just, picturing where area is. So this is an area of a triangle. So 1/2, the height is the height, given by, the y value of this line, 2t. And then we have to figure out the overlap. So it's times 1, the height of the red thing, because it's, nice and, constant pulse. And then t minus 0. So because this leading edge is at t, this is at 0. Okay. Next picture. So between 1 and 2 in t, we get something that looks like this, where we have an overlap with the flat part of the function, of the trapezoidal function, and with the input part. So the input part, we get an overlap that's a triangle because we have this triangular region, times the height here. So we'll get 1/2. Height is still 2t, the point, whatever point we are along here. And then we're going to be at, where does this occur? Well, it's between 1 and t minus 1. So this is the point 1 minus t minus 1 right here, this trailing edge. So that's why we get this thing in brackets right here. Now we also have an overlap of squares. So this is just the area of a rectangle. So the height of it is 2 times 1. And then the width of the triangle is this leading edge t minus 1, because that's where it flattens out. Still with me? Okay. That's good. I'm glad we're following. Because, picture 2 and picture 4 are the hardest pictures to deal with. because it's, there's a change in the behavior of our trapezoid function. It flattens out from a ramp to basically what looks like a step. So you have to, basically add the two area overlap components. Well, the middle picture is probably the easiest one to grasp. So between 2 and 3, this triangle, or excuse me, this rectangular pulse is completely within the flat part of the trapezoid. So it's completely within. So you just get the area of overlap as a rectangle, height 2 times 1 times 1. So even if you could not get, the convolution example right for the other cases, where it's 0 and where it's another constant of 2. So you could at least be able to draw that and fake your way through, pictures 1, 2, 4, and 5. So even if you're really struggling with graphical convolution on the exam, figure out, okay, where can I at least get an area where it's flat? So we have another harder image right here. So this overlap area has two components. So we've got a flat part where it's a rectangular area and a triangle area right here. So the flat part is going to be 2 times 1 times, its width, which is going to be 3 times this minus this trailing edge, t minus 1. So 3 minus parentheses, t minus 1 close parentheses is the width of this rectangular overlap area. Now, this side to the right of 3 in tau land is going to be a triangular area. So we need 1/2 base times height. So we need 1/2 the height. And this is where you have to get a little bit sneaky here. So the height is going to be determined by this line, which is 8 minus 2 times t. You just have to, project this back towards the x-axis, and you'll see that the y-intercept is at 8, and of course the slope is minus 2t because, it goes down 2 for every one you go over. So that's 8 minus 2t, but this is 8 minus 2 quantity t minus 1 close quantity. And you're like, what's going on here? Well, previously, we were matching to behavior to what happened as the leading edge went along. And when the leading edge went along, it was like this. Here now, what the last thing this line is going to see is the trailing edge. So we need to, replace it with the trailing edge formula, t minus 1. And then what is the width of this? Well, this is going to be 1 times t minus 3. That's I guess the base of the triangle. And similarly for the, t equals, between 4 and 5. So here I drew it at 4/5 or 4.5. There's only one segment and it's a triangle for our overlap area. So we get 1/2, height is going to be 8 minus 2t. However, it's, last thing this edge sees is the trailing edge. So it's 8 minus 2 quantity t minus 1 because it's delayed as to when it sees it. And then we get quantity 1 minus 4 minus t minus 1, which is the base of this triangle right here. So we wrote out the overlap areas. Now comes the hard part, which is reducing the cases into things that can actually be plotted. So here we're going to have, okay, this is just t squared, 1/2 times 2t is t times t squared. This right here, okay, 1 minus t minus 1 is just 2 minus t. So we'll get, minus 2t squared plus 2t plus 2t, which is plus 4t, and then minus 2. So negative t squared plus 4t minus 2. 2 is just 2. This thing is a monstrosity to simplify, but it's all arithmetic. It is doable. I guess technically algebra, there's a variable in there. But, arithmetic simplifications. And then this one right here is also arithmetic 2. And of course, we get 0. So if you were to write this out, okay, figure out what y of t is, as you know, just says, find y of t, we could do this. But it wants us to graph y of t. And instead we get something like this. This is like impossible to do without a graphing calculator. So like this would be a little too hard to put on the exam. At least the trailing edge parts, because these are not nice not nice quadratic equations. Now, does this make sense? Okay. Bear with me. Quick check of our work. This x of t right here is like a very poor man's delta function, because we used this as like a delta function approximation before as one of our limiting functions. It would be like, rect 1 of t, where it has a width of 1. And then this is a trapezoid. So when we expect this, if this were a delta function and we convolved them, we would get another trapezoid. But since it's a little broader than a infinitesimally thin delta function, we're going to get something that broadens and smooths out the edges of the trapezoid. And this is kind of what we have. So I would say this is a reasonable answer to get. This all makes a lot of perfect simple sense. Does it? Or are you being sarcastic? Right. Maybe if I wanted to make this a little easier, I can involve something that looks like this with something that looks like, a letter T or something like that. Makes more sense. Well, I'm glad it makes more sense. And like I said, sometimes graphical really is the fastest way to solve a problem, especially if it's like, these sorts of like piecewise steps and ramps. That's generally like graphical is the good way to go. But I should have demonstrated everything with this more complicated example. Even if you see a simpler example on the exam, you're at least more prepared than you would have been if I had shown you something too simple. All right, before I dismiss class, does anyone have more questions? All right, if there's things you want to see on the exam, please go ahead and make a Piazza post, somehow get my attention so I know to add it. It takes me a while to do these examples. Other than that, study hard. There will be extended office hours today, so that, basically all afternoon and evening, you should be able to get in touch with someone to help with your preparations. With that, class dismissed. You want more graphical convolutions? Riyadh wants a 5-question graphical convolution exam. He said he wants more. Oh, you want more practice? Make it a little hard. Bye, everyone. You're welcome. No, you have to have at least one convolution question, Ollie. Like it's a learning objective. There will be Laplace, but like you can't just have Laplace. You have to eat your vegetables too. All right. Goodbye.